All right, we are live. And for those of you who are watching this later, we are not live. All right, so welcome back. This is day 2 of the Virtual Residency Introductory / Intermediate Workshop for 2019. This is our 5th annual workshop, so by now it's an actual tradition. And as we discussed last night, we have at least partial funding for 2 additional years, so we're very excited about that. All right, so this morning we're going to be talking about effective communication. Are we ready? Yes. Are we excited?
Yeah.
All right, hope so. And folks out in TV land, if there's any audio or video difficulties, let us know. Don't be shy. All right, I'm not going to get through all of this, and some of it, in fact, is going to reflect a little bit back to what Bruce is going to talk about in the next session. Some of it will touch a little bit on stuff that others will be talking about in the next couple of days. So I'm going to try and use the time the best way possible and might skip over some of those pieces. All right, so let's talk about research terminology in talking to researchers. So, by show of hands, how many of you believe that oxygen is a metal? Okay, Dana, you're a bringer, so you don't get to vote. All right, so how many of you believe oxygen is not a metal? Okay, how many of you are reserving judgment? Okay, I like that the physicist in the back is reserving judgment. All right, so what do we know about oxygen in real life? Okay, so I'm a lax software developer, so I don't know anything about science or any of that stuff. So I looked this up on Wikipedia, always the best source for all forms of information, and came up with this kind of stuff. And I don't know what any of it means. Well, I mean, I know what the atomic number means, but you know, beyond that, I'm kind of lost, right? You need it to breathe. Fire needs it to burn. If you want to have things rust, you need to have oxygen, that sort of thing. Okay. How about in astronomy? So what is the universe made of? What is the #1 ingredient in the universe?
Dark matter.
Yeah, well, maybe. We don't actually know what it is, right? So let's subtract out and just talk about visible matter. What is the #1 visible matter ingredient in the universe?
Void.
Now that's not matter, that's just the void. What's #1? Say it again. Hydrogen, sure, right? It's atomic #1, and it is, I know what 75% means, and I think I know what mass means. I certainly do not know what the word baryonic means, so, and I'm not inviting the physicists to explain it, because I won't understand it anyway. Stars are made of hydrogen, and so on and so forth. Right? Hydrogen is super important, right? If you study the universe as a whole, when I was a wee lad in grad school, my advisor was a cosmologist. In fact, he's still a cosmologist. So he studies the entire universe over its entire lifetime. So he cares a lot about hydrogen. What's the #2 ingredient? Helium, right? Atomic #2. And it's 24% of total elemental. You can see that I just copied and pasted phrases out of Wikipedia here. I don't know what any of that means. And then, what's the #3 ingredient in the universe, excluding dark matter? For visible matter, what's #3? Everything else combined. Exactly correct. Good. All right. So what are planets made of? What is the Earth, primarily? Huh? So I think that's mostly on the surface, isn't it? Inside. So is most of the Earth on the surface, or is most of the Earth under that? Most of the mass of the Earth is under that. What's the mass of the Earth primarily made of? Hint, slide. Iron is the #1 ingredient in making the Earth. What's #2? Right? And then #3 is everything else. Right? So the outer bits might be the interesting stuff, but the inner bits are primarily made of, more generally, thank you. Okay, excellent, good. So in general, the Earth is made of, and planets in general are made of metals. Agreed? So far so good? Okay. So what is a metal? What makes a metal a metal? Okay, so let's think about this from your grandparents' perspective, right? To them, what makes a metal a metal? Unless your grandparent is a physicist or a chemist, in which case pretend that I didn't ask the question. What makes a metal to a normal human being?
You can smith it.
Huh?
You can smith it.
Oh, I'm talking about normal human beings. What makes a metal metal? How can they tell something is metal? It's shiny. Thank you. That was such a long way to go. Yeah, right. This is the normal. Okay, so look back at the water and coffee and orange juice, right? Which part of that is metal?
Shiny fork.
The bottom and the top, and you know that because it's shiny, right? Kevin, what part of your ring is metal?
Most all of it.
Yeah, pretty much all of it. And how can I tell just by looking?
Color.
The gold color and it's shiny, right? If you're thinking hard, you're thinking too hard. Now, if you're a chemist, you have a very clear idea of what constitutes a metal. I stole this off some website somewhere. I just Google searched for periodic table metals or something like that. And so here's hydrogen, and what does it say right there for hydrogen? It says non-metal. Here's helium, it's the same color as hydrogen, so what do you imagine it is? Okay, and here's oxygen, right above what word? So is oxygen a metal? How many of you vote oxygen is not a metal? How many of you vote oxygen is a metal? Okay, so nobody is willing to admit to oxygen being a metal. Do we agree? There's all these metals over here, right? All the yellow bits. And then this orange stuff apparently is called semi-metals. I didn't know any of this stuff. Seriously, I learned this last week. Right? It's a long time. I took chemistry in 9th grade. It's a long time, right? But to an astronomer, especially to a cosmologist, what does the word metals mean? How do they use that word? Thank you for reading the slide out loud. Very good. Yes. Okay. So again, what are the two biggest ingredients of visible matter in the universe? Hydrogen and helium. So what's the third thing? Everything else. And to first order, thinking about stuff like planets, what are they? Metals. So when a cosmologist says the word metals, what do they mean?
Everything is
Not hydrogen or helium. That's what they mean by that word. Now, when a chemist says metals, they mean this yellow stuff here, right? These elements. But when a cosmologist says metals, they mean neither of these. And everything else from their perspective is all yellow. Okay? Doesn't matter whether it's shiny. Okay. What happens if I get a mathematician, a movie producer, and a psychologist, and I sit them down at a table and say, talk about projection? What's going to happen? Okay, so what is projection to a psychologist?
Projecting your feelings on somebody else.
Yes, believing that someone else is feeling the thing that actually you're feeling, right? What's projection to a movie producer? Right, putting an image on a screen. What's projection to a mathematician?
Representation of a thing onto a plane.
Multiple components of different.
Yeah, moving something from a higher dimensionality to a lower dimensionality, right? So, so they're all using that same word to mean three completely different things. Okay, what's a fluid? How many of you vote you know what the word fluid means? How many of you vote your grandparents know what the word fluid means? Okay, what do your grandparents think the word fluid means? Unless your grandparents are scientists or engineers, then you're cheating. So if you have regular grandparents, what do they think the word fluids means? Liquid. Thank you. Okay. And fluids are those things you drink plenty of when you're sick, right? How many of you have received that advice? Drink plenty of fluids, right? Lots of bed rest, drink plenty of fluids, meaning we have no idea how to solve your problem, but if you wait patiently, it'll go away. Great? Okay. So far, so good? So, day to day, we think of fluids as liquids. In the context of illness, we think of it as drinks, beverages, right? What do scientists and engineers think fluids are?
Anything which flows.
Anything that flows. What is the most important thing that flows from the perspective of many engineers? Most engineers are.
Gas.
Be more specific.
Air.
The air, right? So from the perspective of science and engineering, fluid doesn't mean liquid. Fluid means not solid. So in first order, liquid and gas. And in fact, most of the studies that are done nowadays of fluids, of fluid dynamics, are focused on gases, with the number one gas being the atmosphere, being the air on the planet Earth, right? So when people talk about fluid dynamics, are they usually talking about liquids? No. And in fact, how do you know that they're talking about liquids? No, they don't say liquids. That's the scary part. Anybody know what the phrase is? Incompressible fluid. What does that mean?
Liquid.
Yeah. So incompressible means you can't make it smaller by squeezing, right? So liquids can't be made smaller by, now, of course, if you apply enough pressure, something weird's going to happen. But in normal sort of Newtonian regimes, you can't squeeze a liquid to make it smaller. It's going to take up the amount of space it's going to take up. Whereas you can squeeze a gas and make it smaller, right? It just increases the pressure. Right? And again, I've come to the limit of my science now. So far, so good? Scale. Suppose that your science happens at quantum scale over the course of femtoseconds. In that case, how much do you care about gravity? Shake your head louder with your mouth, Jim.
Not at all.
Not at all. Okay? But on the other hand, suppose that your science happens at cosmological scale over eons, over mega years. Now how much do you care about gravity? A lot, right? In fact, it might be the most important thing in your science. Whereas for these folks, it might be the least important thing in their science. Hey, high energy particle physicists, how much do you care about gravity?
Not much.
Not much. Okay, so actual high energy physicist says he doesn't care much about gravity. What's your physics area?
Solid phase.
Solid. Okay, so how much do you care about gravity? Zero. Okay, physicist, how much do you care about gravity? It depends. Good. You actually made me almost do a spit take there. So, what does it depend on? Yeah, what science you're doing. Because you cover a lot of different areas of physics, right? So, if you're doing tiny things that are fast, not much. If you're doing big things that are slow, quite a bit. Is that fair? Okay. All right. Science versus engineering. What's the difference between science and engineering? What makes science science and engineering engineering? Engineers get paid more. Probably. It probably depends on whether they got the Nobel Prize or not, but yeah, to first order, that's probably true. Although I hear the bioscientists are doing pretty well in industry now. So. Theoretical versus practical. We're headed in the right direction. All right. Although you can have applied science, right?
Fact versus theory.
Fact versus theory. But again, you can have applied science, right? And science tends to be a marriage of theory and experimentation, observation, and nowadays computation and data analysis, right? So all of those things work together, including real life. Was there a comment from the chat?
Scott Turnbull says engineers need to work, but they don't apply.
Okay, engineers need to work with it. Okay, that's fair. Okay. What is engineering preoccupied with that science is not? And what is science preoccupied with that engineering is not?
Science needs to prove things.
Science needs to prove things. Well, so does engineering, because otherwise you get sued.
Kate Adams says engineering has to produce consistent results.
Engineering has to produce consistent results. I'm not going to get into the political debate about whether science has to produce consistent results. I'm just going to assume that axiomatically that science should be reasonably consistent.
Pre-existing phenomena.
Pre-existing phenomena. Not sure how to interpret that. Can you flesh that out?
So in engineering, you use phenomena that you're aware of to produce something new.
Okay.
In science,
You're doing reverse engineering. Okay. Are you an engineer?
I'm both.
Oh, okay, good. Because as soon as you said science is reverse engineering, I immediately thought that's an engineering perspective, right? Whereas a scientist might say, well, engineering is applied science.
It is.
Right? But what makes them different? What do scientists do a lot of that engineers focus less on, and what do engineers do a lot of that scientists focus less on?
Scientists, they do more research, and engineers, they do more testing.
So that, it depends on the context. Engineers are more likely to be in industry where that's true, but if you look at academics, I think that's maybe less true. If you compare apples to apples.
Engineering is applied. Why is science proof?
But science is often applied as well, right? We talk about applied science.
Engineers deal more with what is known, that is discovered by scientists, and scientists want to find something that is unknown and not.
Ah, okay, say that last bit again.
Scientists focus more on what is unknown and what has not been established.
Good, give me a single word that captures all of that in slide.
Trying not to read it.
What?
I'm trying not to read out from the
No, go ahead and do it.
I mean, science discovers, engineers make things.
Yeah, but before they can make them, what do they have to do?
Have to observe.
Yeah, figure out how to make the thing.
I'm trying so hard.
Trying so hard to design it.
Okay, thank you. All right, so it's a D word for each of that. Science focuses on discovery. Engineering focuses on design. Some years ago, I was on the master's committee for an electrical engineering major. And also on his master's committee, in addition to some electrical engineering faculty, were some meteorology faculty. And one of them said, I don't understand how any of what this person has done is research. Because what the student had done was they'd done a bunch of software development and testing. Right? So how the heck is that research? And so we had to patiently explain to this prominent national scientist who has risen to a very, very prominent national role now. So by now, Bruce has figured out who I'm referring to. We had to patiently explain to him that science focuses on discovery, and so his notion of the definition of research was built around discovery, whereas engineering focuses on design, and so an engineer's notion of research is built around design. The thing you make is a prototype for your design idea. So that's a very big difference, and it creates a lot of confusion between scientists and engineers, and when there's confusion, it's often followed with bad blood. Okay, all right, here's a good one. How many of you are computer scientists by background or inclination? Okay. That's your native discipline. Okay. How many of you are computer science faculty? Anybody? No computer science faculty. How many of you know computer science? You're sort of semi-know computer science faculty. So what happens if in front of a computer science faculty member you refer to computer science as IT? Do what?
Eliminate
Who?
the people that did that.
Oh, yeah. I get to walk the plank. I was actually in a meeting some years ago where a bunch of bioscientists were referring to the CS faculty sitting at the table with them as IT. Who would like to predict how well that went over?
It went really well.
Yeah, you're totally wrong. It was terrible. It was very, very bad. Do computer science? Less so. I think among IT folks, the phrase computer science doesn't carry as much emotional baggage as the reverse. Okay. So do CS researchers, do CS faculty do research? I thought their job was just to create software for real research. Oh, right. Sorry, not say that when recording for YouTube later broadcast. Okay, I get to say this stuff because I am computer science, right? From computer science, right? So CS faculty, in fact, do CS research. And CS research doesn't mean developing useful software for the benefit of other people's research in domain STEM disciplines or whatever. That's not their job. Their job is to study computer science, which, like math, kind of lives in between things. In fact, computer science lives in between science, engineering, and math, which makes it super confusing to talk about what it is, let alone what computer science research is. But the short answer is computer science research is what computer science journals publish, right? What, by the way, so does that definition qualify for physics or chemistry? What's physics research? What gets published in physics journals? What's chemistry research? What gets published in chemistry journals, right? What constitutes valid research in a discipline emerges as a consensus among members of that discipline. All right. Years and years ago, I was working with a chemical engineering faculty member. He's no longer at this institution, he's now at another institution on the other side of the country. But I once, in a discussion with him about a project we were working on together, I referred to the output of a simulation that we were working on as data. And he stopped me dead. And he said, no, 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 no. I cannot refer to this as data. Data is observational. This is simulated data. And if I go into a conference and I refer to this as data, I will be laughed out of the discipline. Okay? How many of you think if it comes out of a computer, it's data? Right? It may not be good data, it may not be correct data, but it's data. So to me, that's data, right? And the fact that it was produced by simulation versus an observation, to me, does not change the fact that it's data. In fact, if you're a computer scientist, among other kinds of data, you think of software as data, right? Because software is data to be input into a compiler or an interpreter, right? It's still data. Nobody else thinks that. Okay, so I'm going to take a detour and go in another direction. This is the one that Richard has been waiting for since yesterday. Very excited. Okay, how many of you, remind me, how many of you are from the enterprise IT side, at least originally or recently? Okay, and how many of you, your whole career has been in research computing? And how many of you are other? Okay, and by the way, notice the research computing, whole career research computing is the smallest contingent here. Okay. So, and I think enterprise IT is the biggest contingent. All right. So what's the difference between enterprise IT and research computing? Okay. The biggest difference is in the mindset. So if you're on the enterprise IT side, your goal is what is referred to in the trade as 5 nines. That's 99.999% uptime. That means you're allowed 5.25 minutes of downtime, scheduled and unscheduled. 5.25 minutes of downtime per year. 5 minutes, and I think it's 26 seconds. Okay, so first good.
Technically, it's 16 seconds.
Oh, is it 16? All right, I'll have to run the numbers again. But 5.25 minutes per year of downtime. So what you need in order to accomplish that is everything has to be heard. It's got to be established technology. It's got to be best practices. You need a ton of redundancy. You need to engineer for failover. It needs to be highly secure, right? Heard. On the research computing side, it's literally the upside down of that. So on the research computing side, and I'm not making this up, the target figure is 1.5 nines. This translates to 18.25 24-hour days of downtime per year. 1.5 nines. All right, so how many of you are on the research IT side, or sorry, enterprise IT side? Enterprise IT. Okay, how many of you now, your teeth are on edge? Okay, your skin is crawling, right?
That was like meteorology.
So on the research computing side, we want the opposite. We want to be squishy. We want to be able to change things up with zero notice. We want to use the most cutting edge stuff. In the world of technology, you always have exactly two choices. You can have established technology, which means obsolete, or you can have new technology, which means broken, right? How many of you are in the broken technology business? How many of you are in the obsolete technology business? Okay, those are your choices, right? Typically, there's no such thing as best practices, right? We'd love to have best practices. Why don't we have best practices in research?
They haven't been written down yet.
Yeah, it changes too quickly, right? What are the best practices around the new generation of GPU cards that don't do hardly any double precision floating point, but do tons of half precision floating point? Nobody has the faintest idea, right? That's why they call it research. If we knew what we were doing, it wouldn't be research. So, and I'm not making up this 1.5 nines business. This comes right from the National Science Foundation. They had a solicitation in 2017. It ultimately became a machine called Frontera that is being, I believe, is being deployed right now at the University of Texas at Austin. Frontera, when it's deployed, will be the largest open academic system in the US. And I don't remember what the petaflop rating on it is, but it was something like 20 or 30 petaflops, I can't remember. Unbelievably fast supercomputer. Okay? Not the fastest in the world, but certainly among the fastest. Right? And in the solicitation, this is a $60 million piece of equipment plus something on the order of $40 million for operations. So in round figures, about a $100 million project. For this $100 million project, and this is a direct quote, production resources should be unavailable as a result of scheduled and unscheduled maintenance no more than 5% of the time. 95% uptime, 1.5 nines, right? So I said it and I wasn't kidding, right? So those of you who are on the enterprise IT side, right now, you are cringing, right? And all the blood's draining out of you and everything. How many of you are experiencing that now? Talking about 1.5. Okay, you're making that face like, that's crazy, which is the face I want you to make.
Right.
Okay, and are you thinking that's crazy?
I'm like, what?
No, but that's totally true, right? That's right from the NSF. They're not kidding, right? They're paying almost $100 million for 5% downtime, 18 and a quarter, 24-hour days of downtime per year. By the way, here at OU, we have just slightly beaten 2 nines. We are at 0.9% downtime per year on average. So here's an example from the enterprise IT perspective. This is why enterprise IT people need 5 nines. So 3 years ago, in 2016, Delta Airlines experienced an outage in their primary data center in Atlanta that lasted 5 hours. They reported, so this is not somebody calculated, Delta themselves reported, this cost them $150 million. That's $1 million for every 2 minutes of downtime. So what happened to the people who were responsible for keeping that data center up? They were fired, thank you, yes. Heads rolled, or at least assistant heads, right? So, and by the way, I got a link, this is the real deal, right? This actually happened. So, on the enterprise side, what are the stakes if you screw up?
Very high.
Very high. What's the stakes for the organization you work for? Huge amounts of money. What's the stakes for you?
It could potentially be career ending.
Yeah, it's not just you're fired, you're super fired. Because when you go for the next job interview and they ask you, why did you leave your previous position? You have 2 choices, right? You can tell the truth, in which case will they hire you? No, why would they want to hire someone who does that thing, right? Who has a track record of doing whatever the thing was that caused the Or you could lie, in which case they'll hire you until they find out that you were lying, and then what will they do?
Triple fire.
Yeah! You're never, okay, so at this point, you need to go get yourself a tin cup and some pencils.
Or go work at a university.
Yeah, well. I'm gonna stay out of that one. Right? But if you're responsible for that, you're gone, right? The next day, you might as well walk out the door during that outage. What?
It's during the outage.
Yeah, during the outage, you might as well just pack up your cardboard box of house plants or whatever. Yeah, you're right. Yes.
So yesterday, Google had an outage for 4 hours on the East Coast.
Google had a 4-hour outage on the East Coast.
A lot of stuff was down. All of
Do we know how much that cost? Anyone want to speculate?
they say 55 minutes is like $450,000.
Okay, so that's actually better than Delta if it's only $90,000 a minute. That's way better than Delta. So, still not good, by the way. Okay, so this is why enterprise IT people have the point of view they have. Because if they are not hugely paranoid about this stuff, they're no longer in enterprise IT. Right? Okay, now on the other hand, well, and this is sort of, I was just saying this, right? So let's say that tomorrow's payday and tonight payroll goes down, right? What's going to happen?
Nobody gets paid.
Yeah, and if nobody gets their paycheck, how happy are they? Nobody's happy. And what happens to the enterprise IT people who are responsible for the payroll system? They're gone, okay? Now, on the other hand, on the research computing side, what if we're not cutting edge? What if we cannot meet the research needs of the researchers that we serve? What happens to us? Yeah, well, so we're not going to get fired that day, but over time we become obsolete. They're not going to need us anymore. If they don't need us anymore, then we're fired. Not the same day. It's not like enterprise. But soon enough, we'll be out the door. Right? Okay. So you got to stay on that cutting edge. Of course, when you live on the cutting edge, you bleed a lot. So, what governs the 1.5 nines thing? Why on earth would it be 1.5 nines? Cost. What governs the 5 nines thing on the enterprise IT side? Why is it cost? What governs the 1.5 nines on the research computing side? It's always about the money. So let's do a thought experiment. Let's use OU. So on our supercomputer, on any given day, at any given time, there are typically between 10 and 100 researchers running jobs. Usually it's on the higher side of that, but that's a good estimate. And they're typically coming from 5 to 50 different research groups, on average. Okay. Who does research in academia? Yes? Do you mean yourself, or, sorry, who actually executes the research tasks in an academic research project? The grad students, that's right. The thing that you find out when you become faculty is it was all a lie. When you were in grad school, when you get your PhD, they said, as soon as you get your PhD, you'll be able to do whatever research you want. And you're like, oh, that sounds awesome. And then you get there and they're like, no, you get to write grant proposals, and then you get to manage a team of students. You don't actually get to do anything fun. You get to watch them do everything fun. Is that roughly correct?
A little bit of an exaggeration.
Yeah.
Depends on who you are.
Yeah. So if we have downtime, whose downtime is it? Who's going to be sitting idle during the downtime? The grad students. How much does the grad student make?
Not enough.
I'm going to interpret that to mean you're a grad student. Okay. Anybody know rough figures? What do we typically pay a grad student?
35K a year, that's what it costs.
Well, so I'm not talking fully loaded, just salary. What's the salary for a typical grad student? Okay, 18. So I use 29 because at OU meteorology, I only know this because I'm working on a grant proposal with a meteorology faculty member, so I now know what meteorology grad students get paid. It's $29,000 a year. But yes, it's anywhere from 15 to 35. It's probably a good estimate. Right? Not I'm going to use 29 for calculation, right? So, but as a grad student, you get modest fringe, right? You get typically at most institutions some kind of tuition assistance. It might not be complete, but it's some. And then there's indirect costs. How many of you are aware of indirect costs or overhead or facilities administration? So this is an extra chunk of money that you bring in your grant, but then goes to somebody else and you don't get to spend, right? So think of it as an internal tax, right? And all faculty love overhead, right, faculty member? It's your favorite thing in the world. All right, so let's, when we add all that up, we get about 60K per grad student per year, right? These are round figures. It could be a bit less, it could be a bit more, but it's in that neighborhood, right? So if we have a full 24-hour day of downtime, how much grad student productivity is lost for a full 24-hour day? I'll teach you the way to calculate it. It's the total cost per year divided by the number of days a week, right? So 60K divided by 365 is going to be what, 150 bucks, right? So for each of those grad students, you've lost 150 bucks, right? I guess it turned out to be 160, but roughly that, right? And there's up to 100 of them. So in the event that we have a full 24-hour day of downtime, what does it cost the institution in lost productivity? About $16,000. What would Delta lose if they were down for 24 hours? Whatever, 24 over 5 times 160 million, 150 million. So getting on to $1 billion. Is that right? For 24 hours of downtime, we lose 16K. And that 16K, remember, is sliced and diced among between 2 and 50 different faculty. So how much does any individual faculty suffer in terms of lost productivity? A few $100 bucks, right? Worst case, several $100 bucks. Typically a few $100 bucks. David, do you have a question?
Well, I just wanted to point out the grad students can do something else.
Oh, yes. I'm assuming that they have literally nothing to do while the machine is down. I'm sure the grad students are aware that that's not literally true. There are plenty of things. You know, as they say, if you've got time to lean, you've got time to clean. So get on the Bunsen burners and the beakers. I'm sure there's something you can do.
You can tell your faculty because the HPC was down. That's why you didn't get anything done.
Oh, yeah, yeah. You certainly will use that excuse and blame me when the machine is down. Absolutely. Okay. So the lost productivity associated with downtime is quite modest. Agreed? Okay. Now, if I could offer a faculty member that they would have 0 downtime, or not 5 nines worth of downtime, 5¼ minutes of downtime per year, would they take it? Forgetting about the value proposition, I said, oh, we're going to go from 1½ nines to 5 nines. You guys in? Right? Yeah. Who wants to have downtime, right? But how much more does it cost to provide the same service at 5 nines compared to 1½?
I mean,
Right? So I used to say factor of 2, then the IBM guy mocked me and said, no, factor of 10. So let's say it's 5 to 10 times, somewhere in there. Costs 5 to 10 times as much. So if I want to go to 5 nines, will my budget go up by a factor of 5 to 10? My research computing hardware budget, does it go up by that much? How many of you vote yes, it totally goes up by a factor of 5 to 10?
in an ideal world.
Okay, so do we live in an ideal world? How much does my research computing budget go up if I want to go to 5 nines? None at all, right? So instead of providing this much capacity at 1½ nines, I can provide between 10 and 20% as much capacity at 5 nines. Now, our researchers, our faculty judged on productivity per day or productivity per year? Productivity per year. So if they have a day of downtime, is that a crisis or an annoyance? And if I offer them the choices, no downtime ever, or basically none, in exchange for giving up 90% of your research productivity, will they take that? Will they take me up on that offer? No. In fact, the proof of this, 3 or 4 summers ago, I can't remember exactly when it was, we sent one of our team to a workshop that was I think it was run by University of Maryland, on how to have worse storage for your biosciences. So they were doing consumer-grade disk drives, and on top of that was Linux, on top of that was ZFS, and on top of that was Lustre. That was the software stack, the software hardware stack. And that was super duper cheap. And they weren't just doing it, they were teaching it to the community. Because to them, terrible stuff for cheap is good, right? They don't mind losing, they don't mind risk. They mind not having an enormous amount of capacity, and they don't have the budget for the 5.9 version, right? UT still on it? Because it's starting to make sense.
Yeah.
It's all about the dollars in both directions, right? So I'm not going to offer anyone 5.9s, because the minute I offer them 5.9s, what happens to me?
You're on the boat.
I'm fired, because I can't offer them enough capacity for that 5.9. Okay. Now, here's the good news. By the way, the bad news is it's incredibly hard to be a person who lives halfway in between, to be both enterprise IT and research computing, which I think they just did to you. Is that right? Yeah, they just, how many of you they did that to you? How many of you they moved you from one to the other? So you're 100% on the other side here. How many of you have to live half in one world, half in the other? Is that easy or hard? It's very hard, because every day, several times a day, you got to flip your brain upside down, right? So one year I was commuting back and forth between here and another state that was about a 10-hour drive away. And I was doing this a couple times a month. I did that for about 10 months. And what I found was I'd be having a conversation with someone here, and I'd bring into the conversation something that I'd said to someone there, and the person here, it took me a moment to realize they had no idea who that person was, right? That's the problem that you're dealing with, right? You're trying to keep both things in your head at the same time. How about designing a system to do both well? Is that easy or hard? It's hard, because on the one hand, on the enterprise side, you want to have high reliability, you want your 5.9s, but on the research side, you want the capacity. And the price of the capacity is fewer nines. That's really, really hard to do. Very, very hard. We had a project several years ago when we brought somebody over from the enterprise side to run this research, it was a research engineering project. And he spent about 6 months on it, and he was constantly asking us stuff like, what are your requirements? And we were like, I don't know. We don't have requirements. We want you to guess, and you will be wrong. And he finally punted. He couldn't do it. He had to withdraw from the project, because this notion of, we have no idea what we need, so try something and we'll just see what happens, was just completely the opposite of everything he learned from the time he was a wee lad. But here's the good part of it. Research computing, because we accept things being broken, it's the cost of doing business. Sometimes they'll send us equipment that's pre-broken for our convenience, right? That's fine as long as they help us fix it. But because we accept broken stuff, because we accept downtime, we can be the test bed for new technologies that the enterprise side is going to get to in a few years. We can be the ones who play test. So a really good example is where we went yesterday for the tour. That data center, we were the first ones in there. Why were we the first ones in there? Why was the supercomputer? That's a pretty big system, right? 2 whole rows. Why was the supercomputer the first thing in there?
Didn't know if you could trust the room yet.
Huh?
Didn't know if you could trust the room.
Because we didn't know if we could trust the data center. So what if we moved an enterprise system in there first?
I'm wrong, bad.
If you're wrong, you're fired, right? If the people who built the building screwed up, you're fired, not them, right? They already walked away with their check, right? The building is built. So we moved in first. We told our users we are going to have probably 1, but possibly 2 weeks of downtime. We missed our target by 1 minute. At 5:01 p.m. that first Friday, we sent the note out, the machine's back in business, you can go submit jobs, right? But the users were willing to tolerate an entire week of downtime because it got us out of a much worse data center on the other side of town, which had power and cooling failures once or twice every month, usually taking it out for a whole day, or at least a good chunk of the day. Right? So it was a huge win to give up only 5 more days and then have happiness from there on. And in fact, we haven't had a data center outage that I'm aware of since we moved into this building. So we were the first ones in here. There's another reason too. Have you ever noticed on the enterprise side that every enterprise system is intertwined with other enterprise systems, and unraveling that is incredibly fraught with peril, right? So picking up a system and moving it from this building to that building, from this data center to that data center, is insane.
You build a network without a network.
Yeah, because as soon as you move it over, everything breaks. All of the assumptions that you built into that system no longer apply. So the risk is enormous. So after we successfully moved into the data center, it then took months to get the enterprise systems in there because each one had to be carefully unraveled from all the others in order to be able to move. Some of them they just left and said, we're going to leave the hardware where it is. We're not going to try to move it. And when it's time to move to a new platform, we'll put the new platform in the new data center, rather than try and to unravel an old one. Okay, this is the part that's going to step on yours. So since I'm low on time, I'm going to skip it, and I'll let you cover all this stuff. But I will talk about probability of success. Okay, how many of you vote faculty are crazy? Notice the faculty member has its hand highest. How many of you vote faculty are perfectly sane and have carefully thought things through? How many of you voted live somewhere in between? Okay. So it actually turns out faculty are pretty sane, surprisingly sane. So faculty write lots of grant proposals. Why do they do that?
They want money.
They want money. What do faculty get rewarded for?
Innovations.
Huh?
Getting money.
Getting money. What else?
Writing papers.
Publishing papers and, well, ingenuity is what gets you grant money and papers. Graduating student, right? Those are the things, right? So when you're writing your results from prior NSF support for your NSF proposal, that's what they want the list of. How many students did you get through the system? What papers did you have? In fact, they'd like to see a list of references to the papers that you published as a result of that money, and then they'll give you the next chunk of money. Right? I'm oversimplifying. Yeah, you also have to have good ideas and so on. I've left out a certain thing. But if you don't have that, you're not getting it. Okay, so is it easier or harder to get grant money? Is it easier or harder than 10 years ago? Why is it harder? Right, more people are writing grant proposals, right? So in the olden days, in the long, long ago, even flagship institutions were not necessarily research intensive. Now, many non-PhD granting institutions are research intensive, or at least increasingly research intensive. So the competition is fiercer and fiercer. What else has gone wrong? Politics in what way? That's true, you are a federal employee, so you have to be decreasing. Do what? Decreasing budgets, right? How many of you have heard the phrase flat is the new double? What does that mean?
Flat budgets are going to become common.
Flat budgets now are seen as a blessing, because what's the alternative to a flat budget? Is it a double budget? No, it's a reduced budget, right? Flat is the new double. We feel relieved when they don't cut our budget, right? I'm not going to get into all the reasons why everybody's broke, but everybody's broke. So in order to get grant money, you have to write lots of proposals. And in fact, it's really the law of large numbers. And I will tell you my own experience, the best proposals that I've ever written didn't get funded. And some of the proposals I've written that got funded, I kind of thought sucked. In the sense that I thought, okay, we'll give it a try this year, we'll get some feedback from the reviewers, and next year we'll write a decent proposal. And then they said, oh yeah, we're going to give you a big chunk of money. It's very random. So if it's very random, what do you got to do? Yeah, you gotta do what? Submit a lot of proposals, exactly correct, yeah. So let's take a look here. The NSF, this is the one where I know where to get the data. So the NSF, 24% of proposals to the NSF get funded. From Oklahoma, cyber infrastructure is actually pretty good. Where did we go here? Cyber infrastructure, a third of cyber infrastructure proposals last year got funded. Yes? I did. Woohoo, yes. So you can make yourself look really good, right? Because if you can write a cyber infrastructure proposal, you've got a higher chance. But nobody knows that because they haven't looked at the data. But if you go by state, all right, here's Oklahoma, 16% of Oklahoma proposals to the NSF get funded, 16%. That is the lowest in the country. Is that sad? Okay, well, all right, Guam only submitted one proposal, so but the previous year they reported 100%, so. But yeah, I mean, these numbers, this is terrible. By the way, because my success rate as a PI is substantially higher than this, then I get a big brag when I'm talking to you. It's like, oh yeah, the state average is 16%, but mine is, I think it's like 41% or something. I'm like 2.5 times better than the average for the state. Okay, so if you have some success, you can look good. But it's scary how bad it is. All right, here's another key issue. We talked a little bit about this last night. Research computing has gotten easier or harder? Harder, right? So the systems are more complicated. They have deeper storage hierarchies. They have more hybrid parallelism. So they're harder to use. We talked about this last night. The users, there are more users, more disciplines, and more users per discipline, people who need this stuff. And the mindset is this, right? Android or iOS, the phone, is now their mindset, the handheld. That's their mental picture of what computing is when they show up on our doorstep, right? So what does it take to install software on this? What's the process? It's 3 clicks, right? You click on the store, you click on the app, and then you click to give them permission to listen to your phone calls, right? To first order, that's true. How many of you have given them too many permissions? Okay, yes. And if your hand's not in the air, you're kidding yourself. So how about if you are installing software on a supercomputer? Science application. Hey, what's the process for installing software on a supercomputer? Application software, user software.
Usually download it.
You download it?
Yeah.
Then?
Compile, put it in the public area.
How uniform is the process of compiling?
Usually every application is different.
It's completely random.
Yeah.
Yes, right? So how much labor does it take compared to installing an app on your phone?
1,000 times.
1,000 times more. That might be a slight exaggeration. It might only be 100 times more, but somewhere in the neighborhood, right? It's vastly more trouble. Okay, how about, what does it take to double the storage on your phone? What do you do?
I'll deal with one of them.
Yeah, if you've got that little slot, you pop out the old little micro SD card and you pop in a new one, right? It's that simple. How about if you don't have the slot? You buy a new phone, right? That's how you double your, am I right? That's how you double. How many of you have done that to increase your storage? Right? Yeah, your phone gets to be 2 years old. You're like, I need more storage because now I have lots of movies on my phone, right? And took little videos of my kids, filled up my phone, right? So how do you double storage on a supercomputer? So first you go and pitch to someone to give you the money. How long does that take?
Years.
Yeah, between months and years. Okay. Once you have a commitment on the money, then you have to do sort of a preliminary kind of pseudo design. Then that turns into either a request for proposals or an invitation to bid, something along those lines. Then the bids come in, then you have to evaluate those bids, and you'd better be able to prove that the choice you're making, that your selection is the right one, because the auditors are going to come after you, right? Am I right? Oh, they're going to come after you. Then you announce who you selected as the vendor. Then you go into a specific design phase where you actually work out what it's really going to be. Then you send the purchase order, Then it takes anywhere from a week to 2 months to get the equipment, and then you spend.
Don't forget legally contracts.
Oh, sure, they're going to be in the middle of that. Absolutely, absolutely. It depends who you buy from, because if it's a vendor you haven't worked with before, then the institution has not approved their terms and conditions yet. And the advice that I was given years and years ago was, you never ever sign their paper, you make them sign your paper, right? And then, once it arrives, then you have to physically install it, and then you have to make it useful at the software level. So how long does that take? What's the whole process timeline?
It can take up to a year, maybe a year and a half.
Yeah, my experience has been anywhere from 6 months to 3 years, depending on what the specific thing you're trying to do, right? Compared to you go to the phone store and buy a phone. Yes?
At what point do you start thinking about future-proofing this process?
There is no future-proofing the process. So all the time, and in the sense of you think about it in despair. So you weep, you curl up into a ball, and hopefully you sleep a little bit. When you wake up, the sun is shining, you feel a little better, you maybe eat something or whatever, right? Whatever it takes to make you feel better. You have some comfort food. Yeah, there's no solution to this. Right? What does storage cost? What does storage cost at the phone scale? Anybody know what like a 128 gig micro SD card goes for these days? 20, 40, something like that, right? 2 figures. What does a petabyte cost? So if it's enterprise class disk, and by the way, this is the cheap version, I came up with about 230K for the cheap version, and by the way, single copy. That's not the mirrored version, okay? If I want to do server class disk, I can do that for about 63K. If I want tape, it's about 60. Does that time? Right? But that's orders of magnitude higher than what they're accustomed to. And their mindset of what computing is this.
And like you said, that right there is 5.9 versus 1.5.
Right, yeah. If you were doing it, this would be $1 million out of the gate to get started. Okay. How am I doing on time, by the way? Okay, and what time is our break supposed to start? Do what?
10:15.
No, not lunch, the break. 10:15, all right, so I got about 15 minutes. Okay, so things you can say to a researcher that will make them happy. If you do it this other way, it'll be cheaper than the way you want to do it. Right? Researchers love that answer. I can come up with a solution that's just as good but costs you less money. Researchers love that. Or, if you're willing to pay that much money, here's how much better I can make it for you. Those are in some sense equivalent. Which one do the researchers prefer? What's going to be 90% of your answer? The cheaper one, right? They'd much rather have that. Why? Why do they want to spend less money on their computing? On what?
Students.
On graduating students, publishing papers, and bringing in grant money. Is there any reward for researchers to have good computing? Do the funding agencies reward that? Do their departments and colleges reward that? Does anyone reward that? So the least they can spend on it, the happier they are, because then they can spend their money on stuff they get rewarded. Is that true? Okay. You get to control your part of it. They love that. You can share it with whoever you want to share it with, right? Because they've got collaborators elsewhere. Your students won't have to waste time taking care of this, right? How many of you at your institution, individual faculty, have their own clusters? Okay. Who manages those clusters? The students, right? How trained are they in things like security? So what happens the first day they deploy the cluster? Yeah, it gets breached. Right?
Duplicate IPs, loops, all kinds.
Right, so if you can find a solution where you'll take care of it for them at no charge, especially, they love that. How do you find researchers? Where are they at? Where are the researchers who need you? How do you get them to come out of the woodwork?
They lose their machines.
Oh yeah, right. If they already have a cluster and you turn off air conditioning all over campus, Then you find out who has a cluster. Right? I learned that from a colleague who was at an institution where that happened. I think not on purpose, but it happened, and it turned out there were a lot more clusters on campus than they thought.
Or from an enterprise IT user network access.
Yes, now there are more tools where you can find stuff. Yeah, absolutely. Okay. So how do you find the researchers? Because most of them don't have their own cluster, because clusters cost money and they don't get rewarded for that, right? So it's real simple. You go to your website. You go to your institution's website, and you go look up the college or school or whatever that has STEM in it, and you go to each department web page, and you look at each faculty member's description of their research. And you look for the keywords that indicate they're doing something that's either computational or data intensive. Right? So here are some keywords that, in my experience, and this varies by discipline, but in my experience, are likely to indicate that they are potential users of your system, potential customers. It says computational. In the olden days, by the way, chemists would not admit to this, right? And by the olden days, I mean up to about 5 years ago. The chemists would not refer to themselves as computational. They might say in their research description the word calculations, right? Which meant doing computational chemistry, but they wouldn't call themselves computational chemists, they called themselves physical chemists, right? Now they're more willing to admit it. I'm starting to see faculty listing their research area as computational chemistry, but it's really just in the last 5 years. 10 years ago, you would not have seen that hardly at all. Numerical, that's the most common word you'll find in engineering contexts. They'll use the word numerical to mean they do computational stuff. Parallel mostly shows up among CS researchers. You don't see a lot of that among domain STEM researchers. Informatics you see some of, but that's not much in the physical sciences and engineering. That's more in biosciences and social sciences. And there's lots of other keywords like this, but over time you start to develop a feel for it. Okay, so what do? You send them an email, right? You just send them a cold mail. Janet, I notice on your research page you say that you're doing computational chemistry. So, you know, we have this supercomputer here, and if you and your students would like to have accounts on it, and if you'd like us to set up your favorite software on it and help you learn how to use it, we'd be happy to do that. Right? Does that work? It actually works pretty well. Now, if they're not a good candidate, they'll tell you, well, that's not the kind of stuff I'm doing. We do all our calculations on our laptops. But plenty of people will say, oh, that's very exciting. I had no idea. How many of them even know you exist? Fewer than half, as a general rule, are even aware that you exist. If you're writing a proposal, oh gosh, they love that. When you invite them to be on your proposal, when they can claim that they're part of a grant and maybe even get some credit for it internally toward their annual evaluation with little or no work, oh, they love that, right? Absolutely. Oh yeah. We wrote a proposal. We had, I think, 87 different research teams, so about 95 faculty and staff on the proposal as users, and they just think we are swell. And I was not at the Great Plains Network annual meeting, what was this, 2 weeks ago, last week? But it was much talked about, apparently, that we got the grant and that all these researchers are going to benefit from this and can put it in their own grant proposals. Okay. Ask them what their needs are. What is it that you need? Find out whether that's something and you can't help all of them. Some of them need stuff you can't do, or at least you can't do now. Maybe you'll be able to do it later. If you're, by the way, how many of you are at an institution that has some kind of events for new faculty? Okay, so go, right? It's free food, or at least drink, right? And as a general rule, faculty don't expect the institution's administration to dance attendance on them. And by don't expect, I don't mean they don't wish it were the case. I mean, they don't think it's going to happen. So when you go and pay attention to them, they love that. So you go and you say, hey, we've got this thing, and if you've got research that's relevant to this thing, or this thing is relevant to you, let's get together and talk about it. Now, are you going to get 50 people from that? No, you might get 2 or 3, but that's going to pay off. Go visit your faculty. How many of you like to eat lunch? We're going to be doing an experiment about that. How many faculty like to eat lunch? So what if you offer to take a faculty member to lunch? Find out what it is that they're up to. By the way, how often does a member of the administration ask a faculty member to describe their research? Shake your head louder with your mouth.
Never.
Yeah, pretty much. Now, how often do they come to you and say, tell us about your research?
Very.
Very rarely. So if you, as a member of your administration in some sense, are going to invite them to talk about their research, they're very excited about that. They love talking about their research. Now, they may not know how to talk to their research to someone outside their discipline, but I found here is the easiest way to get them to talk about the research. And we talked a little bit about this last night. You say to them, explain it to me as if I were 12. Most researchers, faculty and non-faculty alike, have never attempted to do that before, and it never occurred to them that that would be something they would try to do. But when you put it in those terms, they can start trying to translate it, and if you give them a little bit of exercise at that, over time they can become quite good at it, right? So Alan Alda, how many of you remember MASH? Okay, Alan Alda runs a national program, has been running it for something like a decade, where he teaches scientists to explain their research in a way that normal people can understand. So he was keynote speaker at one of the recent SC supercomputing conferences, and he showed a video of before and after of a researcher. And in the before video, she was explaining her bioscience research, and she was using all the technical terms, and she was explaining it in a way she would explain to someone in her field. And the after video, she talked about baking cookies. And when she talked about it, when she used baking cookies as the analogy, you were able to follow what the research was. It was an amazing difference that came from, I think, a relatively modest amount of time that she had invested in learning how to refactor her explanations so that normal people could understand them and would be interested in what she was doing. Okay. So I think I'm going to end there. We're out of time anyway, right? It's a break time. I got 5 minutes. All right. So let's use the 5 minutes, 6 minutes. I got 6 minutes. Let's use that for questions. Who has questions for me? I love questions. Yes.
It's a bit of a long question and more directed towards the end of what you were talking about.
Okay.
So I know you said that when you wanted to talk to faculty, you mostly directed your attentions towards the chemistry department, material science, mechanical engineering. And I found
Originally, that's less true now.
Yes. So when you find in these particular departments, there are already faculty over there using computational resources, and eventually new faculty, if they are inclined towards the computational part, would find their way towards us. Albeit a little slower than it would be if you were to directly contact them. But what if you're looking at new departments that originally never had anything to do with computational, and they don't realize themselves that they need to take in this computational aspect and how you reach out?
Good.
For example, like the wildlife department now doing data science.
Well, let me go even farther down that road. The English department.
Yes.
Because now they're doing, okay, so you laugh, but they're doing textual analysis now, right? It's enormously computationally intensive. It's a data problem. So, Jason, you're going to be giving that talk on Thursday or Friday? Friday. Jason will be giving a talk on working with non-traditional disciplines. So I'm not going to try and cover his hour and a quarter in a 2-minute answer. So I suppose my cop-out answer is wait for Jason, because he's totally going to answer your question with way more information than you thought that was available. No pressure. Good. That's a great question. And I notice how I totally got out of trying to an answer.
I'm going to do this Friday.
Yes. But that working with disciplines you have not yet worked with is a very important part of what we're doing. And it's an important part of the communication aspect, right? Because one of the things you're going to have to do is you're going to have to learn enough of their lingo to be able to understand and have an effective conversation. That's why the exercise of explain it to me as if I were 12 is really valuable, because it forces them to use less of that lingo. But over time, you're going to have to pick up some of that lingo. know, and how they use words and what they mean by them. Yes?
Got a question as far as like functionality and help it facilitate the best of both worlds.
Okay.
Enterprise IT versus
Okay.
enterprise IT doesn't really like change.
Right, because change represents risk.
How do you find that middle ground for change management? To engage the researchers who participate in the change management process so that you get both sides are happy.
So there's a couple of different pieces to it. There's sort of a macro and a micro piece. The macro piece is every so often, for us it's about every 4th year, we're called upon to design a whole new cluster, a whole new supercomputer, right? And the technology has evolved in the meantime, and it's going to be significantly different than it was when we bought the last one. So we spend that entire 4 years, we start the design process for the next one the day we send the PO. And yes, in the most literal sense, that's informal initially, but we don't wait before starting to think about that next one. We're already thinking about it. One thing we do here that I think has been very effective is we do an open design process where we invite everybody among our researchers to come to open meetings and discuss what are their specific needs and what are the general needs of the population as a whole. What are the things that they want to see, but also what are the constraints that we're operating under? And by doing that cooperative, collaborative process, they get more buy-in into whatever the result is. So I recommend, and this is something that enterprise folks would never in a million years do, right? You don't want those pesky users mucking around in your design because they'll design it in a way that breaks, right? And you can't trust them to have your needs in mind, where your needs is defined as you don't destroy the very thing that they desperately need, right? Because if you destroy the thing that they desperately need, who will be held accountable, them or you? What if they destroy the thing?
I have to be able to prove
No, it's still you. You can prove it all day long. You're still going to be held accountable. Doesn't matter whose fault it is, it's your fault, right? You wouldn't do it on the enterprise side, but it makes perfect sense to do it on the research side, to bring them into the process. Because they all are going in different directions. They all have different needs. And you've got to find some reasonably good solution that addresses all of those different needs, including evolving future needs that you cannot predict, right?
So basically hurting cats.
It's worse than hurting cats. You're not just hurting the current cats, you're hurting future cats, and you don't know whether they're going to be bobcats or lions, right? And it might be both, right? So you've got to be extremely open, but at the same time, you've got to be thinking several steps ahead of them. Yes, Jim?
Just an observation. I've noticed, when we talk about science EMTs later, in most places, we're asking the enterprise side to help researchers put in a network that is going to be less secure,
right,
and more trusting than everything else that they're in charge
than they've ever done their entire career.
So I think, yeah, more explicitly in the designs that come out, more explicitly, we as researchers, if you're trying to get that put into your campus, you have to somehow give permission to the enterprise IT people that are helping you with this. Give them permission, give them an excuse at the end of time that says, if this breaks, this is on us. We asked you to do this, and you need to please go ahead. We are not going to blame you for anything that
trust us that it's okay to do the opposite of everything every instinct inside you is screaming about.
Yeah, that's an excellent point, because I laughed at my CIO when he told the premise that it's not going to have a firewall, it's going to connect up against I laughed.
And he was right. That's the challenge, right? Everything you've spent your entire career believing is absolutely true, except in this room. And then the opposite is true.
The terms matter too. So a science DMZ, you have what I would call a firewall, block by default both directions.
Right, access control.
But you don't have inspection or any of that high level stuff.
Right.
So there's nothing in science DMZ that says wide open, everybody, everywhere, come on in and beat us up.
Well,
It's
that's not
just-
what the CIO related.
Yeah.
They go back to technology.
That is a different issue.
Well, but in a way, it's accurate because when the CIO said you're not going to have firewalls, it's going to be open to everybody, I agree that's not literally true. But compared to the way you design an enterprise network, it feels like that.
Yeah, the security model is different,
Right.
but it does exist.
So the problem is it's a security model that slams the brakes on inside an enterprise IT person's head. And that doesn't mean it's a bad security model or the wrong security model for research. It's just the opposite of everything you grew up believing.
There's an online question asking Henry to provide the name, contact, or link to the person you mentioned who trains people how to talk to about research to a layperson. Yeah.
Oh, no, I don't have his email address. Alan Alda, the guy who does the how to.
Yeah,
No, this is the guy from MASH. Hawkeye. Yeah, no, he's a celebrity. He
The
doesn't.
center, the Alda Center, if you Google it, they have teams of people that go and, like they did this in Oklahoma State, they had their team come in and work with our researchers on how to explain their research to like 11-year-olds.
Yeah, same basic idea. There's also a group that's at least partially out of University of Connecticut that does something called, I think, science improv or improv science, where they use improv comedy mechanisms to explain science. They teach people how to do improv comedy to make them better at explaining their research. So, good. Next question. Other questions? I love questions.
Yeah, another reference is the EPIC, is that how we
EPIC.
pronounce it now?
The Engagement Performance Operations Center, the newly awarded NSF.
Can you put that in the Google Doc?
But they're like Jason Zarowski and Jen Shop, who are going around doing workshops. We had one at GPN on how to kind of do this with another version of working with researchers specifically for their, all of cyber infrastructure, but their background is networking.
Yes. So you're not completely alone, but sometimes it feels lonely because you're doing something that you know is dangerous and fraught with peril.
Kind of exciting.
Yes. in much the same way that hanging over the edge of a cliff. Right. Exciting. I thought I saw a question over here. Yes.
A comment.
Yes.
The science EMZ sounds a lot like the way the internet was originally designed.
Oh, yes. Poorly, ad hoc, and a lot of random. Absolutely. And research computing in general, that's true, right? And a large part of the reason for that is if we knew how to do it, it wouldn't be research. So we're making it up as we go along. So when we design a new supercomputer, we simply assume that we're going to do the wrong thing. That no matter what we do, the best we can hope for is there's a single moment in time over the 4-year lifetime when it's the right thing. But as soon as that single moment passes, now it's the wrong thing again, right? If we design for 4 years from now, it's the wrong thing now. If we design for now, it's the wrong thing 4 years from now. We just accept going in that the cost of business is it's the wrong thing. Yes?
I would also like to add a comment / question.
Sure.
On an enterprise IT system, usually you have one particular IT system for one specific application.
Right.
But on the research computing side, you have multiple applications on one system.
Right, and I think one thing that's evolved now is on the enterprise side, now you can have a physical system that addresses many different applications, but there are virtual systems within them that are one per. That's relatively recent, right? How many of you on the enterprise IT side have been doing heavy virtualization of most of your stuff for more than 10 years? Okay, more than 20? No, 15? Okay, so it's about 10 years? Okay, so that's a relatively recent innovation as these things go. On the research computing side, that's much less common these days. We're more likely to containerize than to virtualize, but we can do both. But when you're designing a system, you have to design that system so that later you could add those capabilities if you want it. And that's tricky to do. So one of the things we're doing in our cluster is a small subset of the servers, a small subset of compute nodes, will have lots of extra drive bays and extra RAM DIMM slots and the ability to take on GPU cards. And we don't know how they're going to get used, but there's at least 4, if not 5 different things we could do with those servers. And we're designing them to be as flexible as they can be so that as the needs evolve, we can address those evolve.
Yeah, I think that's part of the breakdown is with the trend towards like hyper-converged infrastructure. A lot of the virtualization, people don't realize when you're talking to them, you're trying to sell them a $500,000 piece of equipment. They don't understand that in the long run, this is going to be able to house 400 servers with virtual GPUs, virtual
Sure.
cores. And they don't understand that. Well, I can go and get a server at Best Buy, for $6,000, and you're trying to sell me a $500,000 piece of equipment. Well, I'm trying to serve more than just this one project.
Right, and the difficulty is, from their perspective, they only have the one project. And you are absolutely correct that A, there will be 100 of them who each have one project, and B, each one of those 100 later will have more projects. So you're trying to design for the whole life cycle. They're just trying to get that one thing done. And the question is, are they right or wrong? And that's what Bruce's talk is going to be about. There, I just sold it. I just sold him the bill of goods. But it's going to be fantastic. We keep inviting Bruce back because he does a really good job with this. Okay, so let's take our break. And I'm going to turn off the recording, and then we'll restart the recording when it's Bruce's turn.